Recording. Okay. First day of new material, or real material, I should say. Are you ready for it? Doom, doom, doom. Chapter 1. What a great place to start. Functions. And so I did my undergrad in math, and which means usually people kind of assume, oh, you must have been really good at math. No, not really. Just kind of floated along, and it was the courses that I enjoyed the most. And so I ended up taking more math courses, and then all of a sudden you have a math degree and they kick you out. No, they graduate you. And so, but I was never really, like a math whiz. And so, but I enjoyed math. And functions, a function is one of those funny things where you've probably heard of a function before, right? If you've taken math, any sort of math, you've heard of functions. And for me, I knew it was a term that I should know, and I understood functions. Now, in hindsight, I understood functions, but I just couldn't really get a handle on, what they are. And so we'll start with functions today, lay the groundwork, and hopefully it'll make sense. Okay, so what is a function? A function takes an input and yields an output. Okay? And so if we think about kind of a graph like this, how come my lines are so big? I don't think, no, that's not how I write. Let me see if I can change this. How do I change the... I have no idea what I normally have it at. Maybe like that. Still pretty lofty, I think. This graph became pretty big. Usually if we have something like this, what's the most basic function that we can think of? Probably a straight line, right? And so you might remember straight line, something like this, has a general form of y equals mx plus b. Okay? Y equals mx plus b, even if it's been a while, that's okay. That probably is stirring some emotions, right? Math from the past, okay? Where whatever is attached, or I'll do it down here. So m is the slope. And every time I bring it up, and it's kind of y equals mx plus b season in all my courses. And I mean to look up why it's m. I'm not entirely sure why the slope would be denoted by m. That's just a curiosity thing. But generally, we use m for the slope. Okay, and so m is the slope, but in general, it's the value attached to x. Okay. So you could have ax plus b, or b1x plus b2 if you're in statistics, that kind of thing. So we can use different terms, but what's this b? This b is the y-intercept. And so this is the y-intercept. It's where it crosses the y-axis if I extend this line, because the beautiful thing about lines, hey, where's my pointer? There. Lines is that they continue, right? They continue forever. Negative infinity, positive infinity. And they just keep going and going and going. And that's nice. Here, this is the value when x is 0, and y is b, the y-intercept. Okay. Before I get too carried away, this is the x-axis and this is the y-axis. Okay. And so that's important to remember, because any point in this grid, right, has the format x comma y with round brackets, right? And so we have an x value and a y value, right, for every point in this grid. Okay? And so what this means is x is 0 and y is b, right, just generically. Okay, nice. And you guys seem to be fine with it, but I had a student one time who said, oh, I can't remember the x-axis and the y-axis, which one is which, and obviously it's important. You don't want to mix those two up, right? And so she said, I've got it. I've solved it finally. And so what she said is she imagines a little guy down here on the x-axis, and then the y-axis is a tree that's falling down, and he's down here going, no. And that's how she remembered it was the x-axis. And so whatever you need to do to remember which one is which. But I think that one is by far the cutest kind of rememory technique. Rememory is not a word, but it's cute. All right, so whatever you need to do to remember, do it. Okay, so typically we use x. X in this case is the input. Okay? So I put in a value of x and it yields some value of y, right? And so we have an input. Let's see, what color haven't I used yet? How about light green? X is my input, and once I put it in, I manipulate it with the slope and the y-intercept, right? That's my function, okay? Then I get this output of y. Okay? And so in general, we put our input on the x-axis and our output goes on the y-axis, okay? If we're graphing it. Okay. So, well, we're off to a great start, aren't we? I left this much space. I fear I just squeezed it into a tiny, tiny area. That's okay. Everything I wanted to say. But anyways, okay. So a function takes an input, right, or an independent variable, and it yields an output. The output is a function of the input. Okay, so in the case of a line, right, multiplying by the slope and adding the y-intercept, right, that's the function. Okay, it kind of manipulates your input and spits out the output. Okay. I'll probably think of, oh, I remembered. Now, the important part about a function, okay, is that let me use a different color here. Each input value uniquely determines one output value. And so what does that look like? Well, if I have kind of a set, a set of inputs, and it's pretty common that we just kind of denote generic sets like this, little beans, I guess, with some inputs, right? We don't bother saying, oh, this one is 2 and this one is 6 and this one's 3 or anything like that. Just in general, a function has to look like this. So each input value uniquely determines one output value. What does that look like? Well, it'll look like this. How about this one goes here? All right. Just to throw a curveball, it's allowed to look like this. This is still a function, okay? Because this input yields one output, right? Doesn't matter if it's the same output here as the first item, okay? And then we can have maybe like this and maybe like this. Notice in this case, not all the values went to an output. That's okay. They're potential outputs. So this is a function. Since each input yields a unique output. So here, since each input yields a unique output. What if we do the same thing again? Boom, boom, boom. Can just do 1, 2, 3. A little simpler. What if I try to do something like this? This one and this one. No longer a function, right? Now, things like this exist in math, right? But they're not functions, okay? And so here, right away, right, this is not a function. Since one input yields 2 possible outputs. Since one input. Oh, and I'm realizing I forgot to label these. I'll put it here. Hopefully it was obvious. Input, output. Since one input yields 2 outputs. Today we're talking about functions, right? But just be aware, right, that we will be talking about things that are not functions, okay? We just call them equations, okay? So just as a note, we can work with equations which are not functions. Consider, I don't know, a circle. That's math, right? Think about a circle. Okay. So here, consider a circle. If I have a grid, if I give an input, right, an input, same thing as before, of x, let's pick an x here, right? So if I pick an x that's here, but then I try to map it back to my circle, right, which I can represent with an equation that we'll introduce eventually. Okay. But what do I get? I get two possible outputs, right? Two possible values of y. It's not a function, but we can still work with them. Okay? And so functions are special cases. Okay? And so here, two possible values of y for one input of x. Never doubt yourself. I gave myself that much room and I filled it. Wow. Just had to dig the archives. Nice. Any questions so far? Functions. Haven't really said much, have we? Inputs, outputs, unique outputs. Okay. If we have two quantities, student ID number and the student's 11 a.m. class, okay, is this relationship a function? Okay, and so we've got two different phrasings of it. And remember, just going back to up here, we say that the output is a function of the input. Okay? And so maybe I'll snag that here so we can have it copy. No. Paste. Because then when we read it, okay, is the ID number a function of the 11 a.m. class? Okay? And so which one is the output? In this case, ID number would be considered the output, and the 11 a.m. class would be the input. We change that to 10 a.m. You're all in this class, right? And so if I search your schedules, who has a class at 11 a.m., 10 a.m.? I guess we're here for 11 as well. Okay. Then I would get all your student numbers, right? And probably a couple more because there's other classes going on, right? And so that's not a unique output, is it? Right? And so this one, ID number is not a function. Oh, sorry. You have to like jump up and down outside the window and then I'll see you. Maybe. No, just observe from the window. So the ID number is not a function, right? It's not a function of the 11 a.m. class because multiple ID numbers, right, have an 11 a.m. class. So not a function since more than one ID has an 11 a.m. class. I probably mentioned it last day. My writing was never good, so I'm not going to pretend like it was ever really good, but now my hand's all weird, so now it's really not good. So if there's something that you can't read, and also I get lazy, so it's a lazy factor as well, I guess. If you can't read something, let me know. How about the next one? Well, I have a feeling that it'll be a function, right? kind of how these things go. But let's confirm, is an 11 a.m. class a function of an ID number? Okay. Again, let's map out just using the phrasing, right? The output is a function of the input. And so is this output a function of ID number, which is the input? I would say yes. No surprise, right? But also, right, how do we justify it? Because every student, so every ID number, can only be registered in one 11 a.m. class, and I'm assuming on a particular day, right? We can have multiple 11 a.m. classes, but and so this, yes, this is a function. Is a function since a student can only be in one 11 a.m. class. I'm a stickler for kind of clarifying assumptions, right? And just being aware of, what am I assuming here? So it is, I'm assuming, implied that on a particular day, right? Not just in general. So I'm going to add on a particular day. Yeah.
Would that be true for students who don't have 11 a.m. classes, because there's presumably multiple inputs that are going to lead to that zero value?
I guess that would be another assumption that we're making, is that they have an 11 a.m. class.
Yeah.
Because, yeah, you're right. If they didn't have a class at that time, they would all map to nothing. It's another assumption I think we're making.
Okay.
But, yeah, hopefully that's okay. Trying to think. Yeah. Stick with it. Just trying to think if you could have just inputs that don't map to anything and if that would look different. But that was just me going down a rabbit hole. Don't worry. Let's assume that everyone has a class. So, talk about functions, how they are special cases of just equations in general, right? And so now let's talk about a special case of a function, which is a one-to-one function. Okay? And so sometimes in a relationship, each input corresponds to exactly one output, right? And here's the special case, right? Because that's just, right? That's just a function, okay? And every output corresponds to exactly one input, okay? And so here, earlier, just to make a point, I jumped in and I said, hey, these 2 points, these 2 inputs map to the same output, and that's okay, that's still a function, right? But now for a one-to-one function, they can't do that anymore, right? Because now it has to go the other way as well. So each output has to map to exactly one input, okay? And so here, maybe I'll snag this. Oops. Beep. So here, yes, this is a function, right? But this is not one-to-one. Okay, because of this. So the key part here is that every output corresponds to exactly one input. And so what that would look like is this beautiful, calm back and forth. Oops. Nope. Trying to undo, but they keep changing the shortcuts, or I'm just not very good at using them. But I prefer to blame my my app. Let's do 4. For a one-to-one, I need to have the same number of inputs as I do outputs, right? Because they have to go and map 1 to 1, right? It's kind of in the name. So let's see here. This one, I'll keep it nice and clean. I was gonna go crazy and crisscross applesauce, but this will look nicer. Right? You can, but if you're crazy. This is a function, right? Every input yields a unique output, but it's a special case of a function because now you can also go the other way, right? Every output yields a unique input, right? And so that's the special case of a one-to-one function. So this is still a function, of course, bink, but it's also one-to-one function. Oh, nice. So it's a special case. And we'll parking lot this for a while, right? But later we'll talk about reversing functions, right? And so then we can only do that if we have a one-to-one function. So it's going to come back, right? But you can see how, okay, if it's a function moving from the input to the output, then it looks like it's also a function going from the output to the input, right? Working backwards. Okay? And so that's when we'll talk about inverse functions, but not today. No. Make this a little bit bigger. Usually, we don't like writing very much, right? Especially me. And so we develop shorthand. Okay. And so rather than writing something like height is a function of age, right? Maybe not at my age, but right, because I stopped growing quite some time ago, um, right? But in children, right, it's pretty common knowledge that okay, if you're 10 years old, well, actually, I don't know kids, but if you're 10 years old, I would expect you to be no clue here, right? Yay big, just around here somewhere. I don't know. Um, uh, should have picked an age I know. If you're 1, then you're like this tall, I think. It turns out this is a bad example for me, and it felt pretty simple. So, but when we say height is a function of age, what does that mean? It means I tell you what age they are, just like I did, 10-year-old, and then I output how tall they would be roughly. Right? Obviously, there's a variability there, but in general, right, follows a linear relationship up to a point, up to a certain age, right? Then we plateau. Okay. And so here, age is the input and height is the output. Okay. So what we can do is instead of height, I could, so if we start here, height is a function of age. I don't want to write that out. That's really long, right? And so what we can do is we can replace height with just an H, right? And Usually, if we're doing that, we would define them somewhere earlier, right? If I'm using shorthand for variables like this or names like this, okay? But sometimes if it's obvious, you're allowed to just go ahead and do it. For height, for example, H is fine, and for age, A is fine. Okay? And so we've kind of shortened those up. Okay? But what if we also introduce a shorthand for just function? How about F? Okay? And so H is F of A. Okay? And so height is a function of age, right? Has now been condensed to H is F of A. Okay? Now this is the jump, I guess, that I struggled with. This F of A. Okay? If I have something written like this, okay, F bracket A inside, you read that as F of A. Okay? And so now H is equal to, right, is the same as is. And so H is F of A. Okay? And so you're going to read this as F of A. Okay? But then what you could do is, okay, if H is a function of A, then couldn't you just rename the function H and say H of A? You can, right? And so that's where our function notation comes from. Okay? And so now, how would we read this? This is H of A, okay, which then evolves into height is a function of A. Okay? Back to where we started, which we would read as height is a function of, I said A, but I should have said age. Luckily, they're similar sounding. Okay? So now we have this very nifty function notation, right, giving us a lot more shorthand. Okay, and so function notation in general looks like this. So you have some output, which is equal to a function of the input. Okay? And often we just do this, where we replace just the general function with what the input is. Okay? So, just as a side note, going back to our line that we started with, right, I put in a value of x, and it gives me a value of y, right? But this y is my f of x, right? It's the output when I put in x, right? And so from here, we can replace this y with an f of x, and you can read them interchangeably. And that was a game changer for me. As soon as I realized that I could just read f of x as y, then everything just kind of fell into place. Okay? And so now I'll make a note of that. So f of x is the same as y in y equals mx plus b, which means that f of x can be written as mx plus b. Right? It's just a fancy way of saying y. Right? F of x is the output when you give x. Okay? Any questions before we do an example? Okay. Suppose f is a function where f of holiday returns what month it's in. And what I want you to do, well, you can think about these, right? I give an input of Halloween, and it's implied that I want the output, right? The month that it's in. I'm going to go with October. Okay. The next one says solve f of x is equal to November. Why is that different? Right? Why does this say evaluate? And why does this say solve? They're two different terms. And if you, well, if you read this and you said, well, the output is October, of course, that's cool. And even if you saw this, you would say, well, what month? November. If the month is November, then what holiday is there? Right? We only have one, Remembrance Day. Uh-oh, I have to spell it. X. Remembrance Day. I'll just kind of put a little squiggle through. Remembrance Day. Or, as my mom calls it, Novembrance Day, because she can't keep track. It's bad. Yeah, so it's an American textbook, and so it's meant to have two possible inputs, Thanksgiving and is it Veterans Day, or probably something similar. We only have one. Remembrance Day. I always say it's the coldest day of the year because my husband's in the military, and so we go to the cenotaph, and you stand there, and you're standing there, and you're standing there, and it's so cold, so cold. But it's me complaining. But I always say it's the coldest day of the year. Never do I stand out in the cold for like hours, except for Remembrance Day. So, so even, well, I'm trying to cover these up. So imagine if these words weren't here, right? You knew what to do, right? So you saw F of Halloween, well, it must be looking for the output, right? And then you saw F of X is November, well, it must be looking for the input, right? And so that's the difference between evaluate and solve. Okay? And so evaluate is find the output versus solve is find the input. Okay? But like I said, you don't have to remember that. You just let the question be your guide, right? And it should be relatively obvious what it's looking for. Okay? But that's good to know, right? Words matter, evaluate, solve. Okay? How about this function? C of P is how you would read that, right? Gives the cost, so I think C is the cost, of grooming a poodle weighing P pounds. Has to be a poodle, I guess. Probably now it's more of a doodle. But anyways, cost is the function of P, the weight in pounds. The poodle is a decoy. Right? So you have to interpret C of 20 is equal to 30, right? What does that mean if you had to put it into words? Well, the cost of grooming a poodle that weighs 20 pounds is $30. Okay? So here. the cost of grooming a poodle weighing 20 pounds is $30. Nice. Good. Any questions? We already talked about this, right? But, right, when we work with functions, there are two typical things that we do: evaluate and solve. Evaluating a function is what we do when we know an input and we use the function to determine the corresponding output, right? And so evaluating, because it's a function, will always produce one result, right? Each input can only yield one output, okay? And so versus solving equations involving a function is what we do when we know the output, right? And then we have to map it back to find the input, potentially more than one, right? That's allowed. If it's a function, it's allowed, okay? Not if it's a one-to-one function, right? But that's a special case, okay? And so that would produce that output. So solving a function could produce more than one solution, since different inputs can produce the same output. Well, in this case, I can't remember what I was going to put there. For real this time. Can I make something up? Clock's ticking, Emily. No, I can't. That's okay. We'll just move on with our lives. But it gives me more space to do these guys. One way that we can represent a function, right? Very basic way of representing a function, and not a very fun way, is as a table. Okay? And so what we can do is we can say, okay, the table below defines a function q, so just generic q, which is a function g of n. So the name of the function is g. Okay? And just as a general rule, we use f for function, and then g, and then h commonly. Right? We kind of stick to the, it's not the middle of the alphabet, but kind of like later beginning, right? For some reason. And so f, g, h, if we have multiple functions, those are common names, generic names. And in this case, n is the input. And so what we have is we have some input n, and it gives us the output q. First of all, is this a function? Is this a function? What are you looking for? Each input has to yield a unique output. Right? So 1 goes to 8, 2 goes to 6, 3 goes to 7, 4 goes to 6. Is that going to be a problem? Both of them going to 6? It's not one-to-one, because, so I think the easiest way to visualize this is to have your input and your output. And you can have 1, 2, 3, 4, 5. And your outputs, your possible outputs seem to be 8, 6, 7, 8. How about that? So now 1 goes to 8. Oh, this is going to get messy, isn't it? 1 goes to 8, 2 goes to 6, 3 goes to 7, 4 goes to 6, and 5 goes to 8. Hmm. I'm going to go with, it is a function, but it's not a one-to-one function, right? And so this is that sneaky scenario where, okay, 1 and 5 both go to 8, but that's allowed because 1 only maps to one thing, right? And 5 only maps to one thing. But it's not a function moving the other way, right? And so this one is a sneaky one, but it is okay, right? And so yes, it is a function. Whee! Which means we can evaluate and solve. Yeah? Nice. Okay. Oh, but I'll add, but not one-to-one. Sad face. That's a special case if it's one-to-one. Right? Doesn't always happen. So what if we have to evaluate G of 4? And now that I've given myself all this room, G of 4, I give an input of 4. And what am I looking for? I'm looking for the output. When the input is 4, I get 6. And so G of 4 is 6. If I have to solve these two, let's start with G of n is equal to 7. Now I know my output is 7. So I scan here and I look for my output is 7. And there's only 1, and so it maps back to 3. Right? And so then I would say n is 3. How about G of n is equal to 8? I have 2 8s here. Right? That's okay. Just means that n can either be 1, 5. Right? Nice. So this one, little bit sneaky. Hey, what happened to my line? 5 goes to 8. A little bit sneaky. Does each table represent y as a function of x? Right? So y is the output. And x is the input from that phrase. And so if so, let y be f of x, right? So y is the output still, and we're going to evaluate f of 2, and we're going to solve f of x is equal to 4, right? If it's a function. Otherwise, we can't do that. Okay? So, all right, let's see here. Looking at our outputs might be the best place to start, right? If we have multiple outputs, right, then we just make sure, right, that it's allowed. Okay, so I have 4, 7, and 4. And so 2 gives a 4 and 6 gives a 4. I'm okay with that. Right? Imagine how the lines are going, right? And so if 2 is going to 4, but also 6 is going to 4, that's okay. Right? This one is a function. So I've got unique outputs, 754, but, so then I move into my inputs. This is a problem, right? 4 gives me 5, but also 4, right? So not unique outputs. And so for this reason here, not a function. Right? 4 isn't allowed to split up and go to 4 and 5 at the same time. Right? 2 is okay. 2 goes to 7. That's okay. Right? But it's this input of 4 that gives us trouble. Yeah? Now I'm back to unique inputs. That's nice. 2, 4, 6. And I also have unique outputs. Wow. What would this look like? If you did your, I don't know what to call these little, I think I've heard them called beans before, but I don't know, sets. If you did this, right, 2 goes to 7, 4 goes to 5, and 6 goes to 4. This is not just a function, but it's a one-to-one function. Nice.
How many routes do you have?
Oh, yikes. No, I don't, but
I guess.
oh, nice. Oh, yikes. You're okay. You're right. Math must go on. No, if you need to run to the bathroom, please. So this is a function, and it's a one-to-one function. Special case. If it's not a function, we can't do anything with it, right? In terms of evaluating and solving, that's okay. But if it is a function, we're going to let y be f of x, and we're going to evaluate f of 2. So over here, I'll do part A, f of 2. If I give an input of 2, I get an output of 4. And I want to solve f of x is equal to 4. If I have an output of 4, there are 2 possible inputs that make that happen. So x is either 2 or 6. Nice. Do the same thing for this other function. F of 2 is 7. And if f of x is 4, my input must be 6. And there's only one. Nice. So tables, using tables as functions, I think is kind of fun. Right? They're not very elaborate functions at all, right? But you can visualize them pretty easily like this, right? And kind of see them happening. Usually, our functions are shown as graphs. Right? And so one thing that we can use is called the vertical line test, or the VLT. The vertical line test, okay, it is a handy way to think about whether a graph defines the vertical output, which is your y, okay, as a function of the horizontal input. Okay? So really what that's saying is it's a way of seeing if a graph is a function or not. Okay? And so how it works is if any vertical line would cross the graph more than once, okay, then the graph does not define only one vertical output for each horizontal input. Now that's a long way of saying the graph is not a function, right? And so I'll bump this down and clarify, because that's pretty lofty stuff. And so if a graph passes the VLT, the vertical line test, then the graph is a function. So the vertical line test, so a vertical line goes up and down like this, right? And so a vertical line moves up and down like that, right? As opposed to a horizontal line, right? And how I remember that is the horizon, right? If you're watching the sunset or the sunrise, like this. So it's like this, and then you just have to remember one, and then the other one is the vertical, right? And so a vertical line looks like this. And what you're going to do is you're going to imagine a vertical line slicing at every point of the graph. And if it ever hits multiple points in the graph, it's not a function, right? Because as we saw in the circle, right, then you get two outputs, right? But we have to have just one input. And so what this looks like, let's draw. This one is kind of tricky because it's so tight, and I'm not very good at drawing vertical lines. But no matter how tight they are, these curves, it keeps moving on. Oh, things got weird over here. Let me try again. Ding, 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 ding. Keeps moving. Right. So I only cross the graph at one point, right, for every value of x. And so here, this is a function because it passes the vertical line test. I wish it had started with this first one. So a line, if I imagine some vertical lines, I don't see any point where it's going to cross more than once. And so again, this is a function because it passes the vertical line test. And I guess I already gave it away, the circle. Circles exist, no doubt about that. Right? We even have equations and we have math to work with circles, but they're not functions, right? So right away here, not a function. Oops. Not a function. I tried to combine the two. Yikes. Not a function because it does not pass the vertical line test. So from tables, you can determine if the table represents a function. From a graph, right, using the vertical line test, you can determine if it represents a function. Right, so there's lots of ways to determine if you have a function or not. The horizontal line test, or the HLT, now we're drawing horizontal lines. What does that do? Just like before, right? Just like here, we were able to determine if we had a function using the vertical line test. If it is a function, then we can take it one step further and see if it's a special case, if it's a one-to-one function. And so that's what the horizontal line test does, right? And so the horizontal line test right? Once you've determined that a graph defines a function, so it passed the vertical line test, right? Then an easy way to determine if it's one-to-one is to use the horizontal line test, which works the exact same way, right? You're going to draw horizontal lines like this through the graph. If any horizontal line crosses the graph more than once, then the graph does not define a one-to-one function. And that's okay, it's just not one of those special cases. Okay? And so here, let's draw some horizontal lines. Okay. This was a function, so now we're going to check. I'll eliminate this one already. We already determined it's not a function. And so it can't be one-to-one. Right? But we will focus on these two. This is a function. And we said this is a function. So now, once we have a function, draw your horizontal lines. It's looking good up here, but then when I move down here, all of a sudden, I'm crossing not one, not two, but 3 times, right? And so it's not one-to-one. Okay? But it is a function, but it's not one-to-one. Whereas a line, bing, 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 looks good. I'll only ever cross once. And so this is one-to-one. Nice. So for us, for graphs especially, right, using the vertical line test and the horizontal line test saves us a lot of time. Which of these are functions? So if we're looking for functions, in general, what do we use? We use the vertical line test. Start here, then crisscross. Yeah. And so I like to just imagine them. This one looks good. Just do a check mark. Huh? This one looks bad. I only have to draw one or imagine one. Right? Not a function. This one is sneaky, but I'm going to go ahead and say that it keeps moving and it passes the vertical line test. You know, sometimes they get kind of squished like that, but that's okay. And here I can see, let's see here. I can see an example where it doesn't pass, so immediately it's not a function. Oh. Nice. We can take it one step further because now these two are our functions, but this one is not one-to-one. Right, if I move on to my horizontal line test. And so here I'll say, but not one-to-one. This one, right, gets a little tight around the origin there, but I would say it is one-to-one. Just by glancing at it. Nice. But this one. So using this graph, if we want to evaluate and solve something, then what's the first thing we should probably do? Make sure it's a function, right? And so let's do that first. I can't find any spot where it's crossing more than once. And so I'm going to go ahead and say it is a function. And just to keep it kind of clean, I'll erase those, but it is a function, right? And so now we can evaluate f of 1, which means if I give it an input of 1, what's the output? Yeah. Now with these grids, we'll do approximately or approximations, right? It's just for quick eyeballing, right? And also a note, whenever we have graphs like this, you always assume that they keep going, right? So they keep going and going and going, but we're just working in this little area. Okay. And so if we want to evaluate f of 1, then 1 is the input. Okay. And so here, let's do it in green. The input is 1, and it gives me an output of roughly 3, let's say, right? I'm not going to bother too much with, if I had to guess, I'd say 2.8 or something. And so here, part A, f of 1, and because I'm approximating, I'll say approximately 3, right? Roughly equal to 3. And so here, this is approximately. Just rough approximations is good. All right. I'll circle A with green, and then I'll do B in blue, I guess. If I want to solve f of x is equal to 1, without remembering what the term solve means, if I look at that, I'm probably looking for the x's that yield an output of 1. Okay? And so what am I going to do? I'm going to look for the output of 1. Okay? And I'm going to span across here and look for all the inputs that give me an output of 1. Well, I see there's here, here, here. Okay. So there are 3 inputs that yield an output of 1. So x, again, I'm just approximating here. X is roughly 0, -2, and -4. Nothing too crazy. Nice. Any questions? You knew it was coming. Not just graphs and tables, but how about formulas as functions? Yeah. Okay. If we have a p, which is a function g of k, okay, which means that our k is our input and g of k is our output, but our output is now called p for some reason. Okay. Then we can use this formula to evaluate g of -2. What does evaluating g of -2 look like? Well, here, let's see. G of -2, I'll start with my g of k formula generically. 3k squared plus 1. I plug in a k of -2. So g of -2 looks like this. 3 times -2 squared plus 1. What we should do, though, is just talk about in words what this formula does. Okay? And so g of k takes an input k. First, it squares it. So first you have to start, so like the inside of an onion, right? And then you work out through your layers. And so you're going to square your k, then multiply it by 3, and then add 1, right? Working your way out through those layers. And so it takes an input k, squares the value of k, right? K to the power of 2. Multiplies that value by 3. Multiply that value by 3. And then finally, step 3 is add 1 to that value. And by that value, I mean the previous value, right? It's morphing as we go. And then I'll just say add 1. So now if k is -2, first thing we're going to do is we're going to take -2 squared. -2 squared is 4. So I get 3 times 4. Careful on your calculator. Squaring any value should give you a positive value, okay? But some calculators, if you do -2 to the power of 2, it's really just squaring the 2, right? Which would be like -2 squared, which is -4. That's wrong, right? Because you want the -2 all to be squared, right? So either just drop the negative or put the -2 in brackets before you square it. Both are good options. But as long as you remember that any value squared has to be positive, right, then you're okay. So now I have 3 times 4 plus 1. 3 times 4, going to go ahead and say is 12. And then plus 1. 13. So g of -2 is 13. Or if you want, p is 13. Right. So, or p is 13. That's extra. I don't know why they bothered defining p, but anyways. Okay. What if we have to solve g of k is equal to 25? Uh-oh. So we're given g of k. Let's just start with our generic g of k is 3k squared plus 1. We're told g of k is 25. So what I'm going to do on this left-hand side is I'm going to replace it with 25. Now I have 25 is equal to 3k squared plus 1, and I want to solve for the k that makes that happen. So let's see here. 25, well, what do I have to do? So before, we had to start inside when I plugged in the k, and I had to kind of bloom my way out. Now, if I want to solve for the k, right, I have to pick away from the outsides until I get to the k, right? And so I have 25 minus 1. All right. So subtract 1 from both sides. So I have 25 minus 1 is 3k squared. So 24. Then 24 divided by 3. I have to divide both sides by 3. So 24 divided by 3 is what? 8. I've got some go-tos. 3 times 7 is 21. Add 3. Sold. It helps that I have the head knot going on here too. So 8 is k squared. How do you undo that square? Or square root. Nice. Now, be careful, because when we do the square root of both sides, what happens? We have to add on that plus minus, right? Because we get 2 options. We think about, just think about 2 squared is 4 versus negative 2 squared is also 4, right? So we have to attach that negative, that plus minus on there when we take the square root, right? So that's the only caution there. Okay. And so here we need plus minus when we take the square root. Otherwise, besides that, we're off to the races. All right, k squared, square rooted, just gonna give me k. All right, but I do have the plus minus root 8, which feeling like is gonna be a weird number. Let's see here. Well, 2 root 2, huh? Well, so on your calculator, it usually gives you the exact answer, right? So it simplifies to 2 root 2, which is the exact answer, same as the root of 8. And so here we get the root of 8. So the plus minus root of 8 is equal to k. All right, we kind of dug away at that k. And the plus minus is being handled over here. And so adding it here is kind of redundant. So we do have a k, an answer for k. And this is what we call the exact answer. This is the true answer, right? The exact answer is just plus minus root 8. Okay? Or 2 root 2 plus minus 2 root 2 from your calculator. Okay? From your calculator. I don't just do that. My calculator does it, and yours probably does it as well by default. Now, if you want the decimal version, okay, you press the S backward, forward arrow D. I don't know what standard form to decimal form, maybe? I don't know. The S, I don't know, but D, I assume, is decimal. And so we get roughly, k is roughly, so when I show, oops, the root of 8, unless I have all the decimal places written down, which I don't want to do, okay, I'll just write down what is showing, plus minus 2.828427125, but keeps going, right? I just don't know what they are. That's okay. And so now this is what we call, I use an approximately equal since it's an approximation. So this is the approximate answer. And just, I'll make a side note here. Use, I should have done my SD button to show decimals on your calculator. Somewhere in my pictures, where are they? Here, maybe. I have a picture of my calculator, but it's been a while, I guess. Got the most boring camera roll there ever was. I'll have to dig it up for next time. But anyways, the SD button does it. Oh. Nice. And you can practice storing it. Storing this number. If you have to use the root of 8 later on in your calculations, how about we do that? To store the exact value of the root of 8, we'll just use the positive version. You do the root of 8 on your calculator, right? Get it on your screen, and then I think we have the same. I hit the STO button. Store. It pretends it's not doing anything, but it is. And then you have, you can press A, B, C, and tell it which letter to store it in. And so usually, these are all memory slots. It's kind of hard to see A, B, C, D, E, F, but those are your memory slots. Okay. You can also look at your entire memory. I can't remember what you put where. And as you store things, so usually I just store things in A until I don't need it anymore. And if you overwrite it, it just overwrites it. Okay. And so I'm going to store it in A. And it should look like the answer in A is 2 root 2, something like that on your screen. So on your screen. And then to recall, then you can clear your screen and you can go shift, recall, and then it shows all your memory and hit A. So you can hit shift, recall, oops. And then A. A. And then equals. And it should say 2 root 2. Right. So now you can do something like 3 times recall A plus 1. I get 1 plus 6 root 2, right? Using that exact number. We'll do more practice with that because it's going to be important. Okay. Just enough time to do our toolkit functions. Okay. Let's see here. So in this course and in any math course, we have this list of toolkit functions. Okay, and so just like how when you look at this shape, you know the name of this shape is a triangle, and you know the name of this shape is a circle, and you know the name of this shape is a line, right? We need to build that a little bit further. Okay? And so just imagine that these are all just new names of shapes with some functions that are attached to it. Okay, and so these math functions all have shapes that we need to be comfortable working with. I'll move these over here. So the toolkit functions, we can start off nice and breezy with the linear functions, and a linear function can be as basic as a constant, right? Where f of x is equal to c, where c is a constant or a number. Okay? And what I want to do here is trying to decide. Well, either way, I have to add a page. I'll add a page here. I'll move this. There. But I also posted on Moodle, or I made it available rather. There's lots of hidden things. Mostly stuff I don't use anymore. So don't worry. The graphs of the toolkit functions are in the textbook and other resources section of Moodle. And so what I'm going to do is I'm going to just bring this in. Can I copy this? I wonder. Add a page, copy. No. I just wanted. Sure. Copy. Hey, why isn't it pasting? Paste. Oh, I remember, actually. I'll just go through it again. There. I did it. So instead of just talking about what the toolkit functions look like, but here's a list of them, it'll be more important to know, or I guess look like in the sense of their functions, right? It'll be more important to know what they look like in terms of their graphs. Okay, and so we can start with something like f of x is equal to c, and what does that look like? It looks like this. Okay? Just a line, but it's a special case where if f of x is equal to c, or if in this case it looks like f of x is equal to 2, right? Then it doesn't matter which input I give, the output will always just be 2, right? So it's just a horizontal line. Very boring, but it exists. Okay? More interesting is maybe f of x is equal to x. right? Or we've seen mx plus b, right? But mx plus b has the same shape. It just moves up and down and maybe tilts a little bit, right? Depending on the slope and depending on the intercept, it might move around. But it has this general shape, okay, of f of x is equal to x, right? And so that's what we're going to keep in mind is these are general shapes for something where the highest power of x is just 1. Okay? That'll be more important down here. Okay? The absolute value function, okay? You might recall the absolute value function basically drops the negative. It does a little bit more than that. We'll work with the absolute value function, but effectively, you just drop the negative, right? And so if you have the absolute value of -2, then you get 2, right? And so that's why the input, if you have +3, you get an output of +3. But if you give an input of -3, you get back to +3. So you get this V shape, right? Notice how it's just f of x equals x, but then folded up to be positive outputs again. Right? And again, we can do things to the absolute value of x, right? We can maybe make it the v tighter or flatter, move it up around, left, right, things like that. But the general shape stays the same, right? F of x is equal to x squared is called a quadratic, okay? And it looks like this. Parabola, might be familiar with it. Okay? Now, the beauty of these kind of higher functions, I think of them as, right? Because here you have a power of 2, x to the power of 2, and x to the power of 3, right? Even if you add in something like f of x is equal to x squared plus x plus 4, if the highest power on x is 2, the overall shape will always look like a parabola. And so that's cool. So knowing what an x squared looks like, right? You also know what something a little bit more complicated looks like overall. Yeah? And so I'll use Desmos quite a bit. You guys use Desmos before? Maybe sometimes, yeah. I know some high schools use it and some high schools don't, and that's okay. It's just a free app, and I use the graphing app, but also, so there's the, it's this one that I use the most for graphs, but this is a nice calculator, and they're both free. And so if I need to show my calculator work, I'll do it in that app. I don't know why it's, boy. Okay, I'm going to close it. Do the age old, now it works. Shut it down, start it back up again. So if you have something like x to the power of 2, and as you add things in, it just kind of jumps around and until you settle down on something. But x to the power of 2 looks just like what we saw, right? General shape. Now, if I do x to the power of 2 plus 3x minus 4, right? Something more complicated, but the highest power on x is still 2, right? Look at this. Same general shape, right? And so knowing that general shape is going to be really, really useful. What if you do something crazy, like a negative? Well, same shape, just look, flop down, right? Same shape though, right? And so getting to know these toolkit functions, as we call them, or I call them, and the textbook calls them, it's going to be really useful in just figuring out general shapes of functions, right? And that means what? That means I can know what a reasonable answer might be, right? If I can visualize this shape, then I can say, oh, that seems like a reasonable result, right? And so that's what we're working towards. Okay? So as long as the highest power of x is 2, it'll look like this. Okay? If the highest power of x, right, and you can sprinkle other things in there, you can get crazy, right? Even something like f of x is x to the 3 minus 2x plus, or I guess let's square that one, plus 9x minus 2. It'll still have this shape. That's not very telling, is it? But it's kind of going in opposite directions. Right? And so I can't explain it. That's the sound it makes, I guess, in my head. So x to the power of 3, right, looks similar to a parabola. What's happened? It's just that this little guy is just kind of going down this way now. Right? If you flip this arm up, right, you get x squared. But that's the difference. And so we'll have this kind of smooth S-like shape for x to the power of 3. Okay. And nice. Again, you can look in Desmos. You can try it. X to the power of 3 looks like that. Okay. And you can zoom in, and it looks like it might be flat, but trust me, it keeps going up and up and up and up and up, and it keeps moving through the origin there. Okay. What if you do something really crazy? 3x to the power of 3, oops, to the power of 3 minus 4x squared plus 3x minus 9. Now I've really done it. Some stuff happened. Maybe the minus 9 was a bad idea. Minus 2. Now they're easier to compare. Maybe. No matter how much junk you throw in there, the overall shape stays the same. All right. That's cool. What about the square root? When we don't have a number in the crook, it's assumed, I call this the crook of the root. I'm not sure that's a technical term, but I should confirm. But when we don't have a number, it is assumed to be 2, but I just wanted it to be really clear that it is the square root. Okay? And so the square root of x is kind of a special case. Okay? Because what does this look like? Well, the only inputs that I can put into the root of x is I can only put in positive values, right? And so what this shows me is that I can only take the square root of positive numbers, or on the flip side, I can't take the square root of a negative number, right? And so here, notice we can't take the square root of a negative. We didn't have restrictions like that on our x squared and our x to the 3, right? We did have restrictions on our outputs. Just like we said earlier, if I square a number, then the output will always be positive, right? And so that's what we see in this graph. Okay. If I take a number to the power of 3, right, I preserve that negative. If I take negative 3 to the power of 3, right, I get a negative number back. Well, I don't see it on here. Negative 2 to the power of 3 is 8, but it's off. Negative 8, but it's off the charts. It's okay. So these graphs show us the possible outputs as well. But the cube root is the third root, and it looks like a twisty version of x to the 3. Right? Got a similar shape. Some stuff happened here, right? But it can take negative and positive inputs, and it yields negative and positive outputs. And so that's cool. What about the reciprocal? 1 over x. 1 over x looks like this. The is the asymptote. So here, in this case, we have an asymptote at x equals 0. In this case, it's at x equals 0 because we can't divide by 0. Dividing by 0 is undefined. It's illegal math, right? And so since we can't divide by 0, okay, it's undefined. Oops. Or as I call it, illegal math. Oops. 3 L's. Illegal math. That's illegal in English. Illegal spelling. It's not always at x equals 0, right? This asymptote, right? But anything that has 1 over and then the highest power of x in the denominator is just 1, right? Looks like this. But you could have something like, let's try with 1 over x. Okay, looks like that, just as we expected. What about 1 divided by 4x minus 3? Still the highest power of x in the denominator is 1, right? Just x, 4x minus 3 is still a version of x, right? But now it moved my asymptote, right? I wish I could, maybe I can pick the colors. Can I? Oh, wait, no, I want to show it. Okay, it doesn't look like I can. They're too similar for me, but so I clicked this here and it made it disappear, but what if I hold it? Aha! Let's try. Nice. There, that's better. So now it moved my asymptote. The general shape stayed the same, right? But where did the asymptote go? It's kind of getting ahead of ourselves, but it went to wherever 4x minus 3 is equal to 0, right? Can't divide by 0. That's still the rule, right? And so the asymptote just moves to the value of x that makes 4x minus 3 equal to 0. Right? Nice. And same thing with 1 over x squared. If x squared is in the denominator, right, then we get this kind of all positive output still with an asymptote because x squared can't be 0, right? And so we'll be working with these toolkit functions quite a bit, and I encourage you to just read through them. Let's see if I missed one. Quadratic, cubic, reciprocal. And we did, okay, they're all on there. Phew. All right. Spend some time getting to know these functions and their general shapes. Because like I said, in order to make sure that an answer makes sense, it's going to be really valuable. Okay. I didn't have any more time anyways. All right. If you have any questions, let me know. Otherwise, whoa, I don't see you till Tuesday. Well, enjoy your weekend. See you on Tuesday. Stop this. Oh, maybe.